So today we're going to dive into a really fundamental problem in computing and the absolutely brilliant solutions that let our devices do, well, everything at once. This is the story of how a CPU learned to multitask.
I mean, really think about it for a second. Right now, you might be watching this, maybe downloading a file, you've got chat notifications popping up, and all the while your computer is running who knows how many processes in the background. So how does that one single brain, the processor, keep all of those balls in the air without dropping a single one? Well, let's find out.
To really get how we got here, we have to go back to the beginning. Back to a time when computers faced a very simple but really profound dilemma. Okay, so meet our main character for this story, the Intel 8086. This was a groundbreaking chip from the late 70s, and it's basically the granddaddy of the processor that's probably in your computer right now. For its time, it was a beast, an absolute powerhouse. But it had one huge limitation. It had a one-track mind. It could only do one single thing at a time. You see, a processor is perfectly happy just running down its to-do list, its main program, one instruction after another. It's in its own little world. The real problem kicks in when it needs to talk to anything outside of that world, like a keyboard, a mouse, a hard drive, anything. So the most basic way to handle this is something called polling. Just imagine you're writing a super important report, but you're also waiting for an urgent email. Polling is like you having to stop writing every 10 seconds, check your inbox, see nothing, and then go back to your report. That is exactly what the poor CPU had to do. And yeah, this is an absolutely terrible use of a powerful processor. It's spending almost all of its time not actually processing anything, but just asking, hey, you got anything for me? How about now? Now? It's the computing equivalent of, are we there yet? This was the core dilemma that just had to be solved if computers were ever going to get better. And the first big breakthrough was this really elegant idea that completely flipped the script. What if instead of the CPU constantly nagging the outside world could just tell the CPU when it needed something? So instead of that incredibly wasteful polling loop you see on the left, engineers introduced a new piece of hardware, an interrupt controller. Now the keyboard doesn't just sit there waiting to be asked. When it has something to say, it sends a signal. And that signal is called an interrupt. It is the perfect name for it, because it's basically a doorbell for the CPU. The processor can now just focus on its important work, totally confident that if something happens, like you pressing a key on the keyboard, the doorbell will ring. And here's how it works. The doorbell rings, the CPU immediately stops what it's doing. But first, it puts a bookmark in its work so it knows exactly where to come back to. Then, it runs this special little procedure to handle whatever rang the bell, like grabbing that character you just typed. Once it's done, it goes right back to its bookmark and picks up its main job like nothing ever happened. This seems simple, but it was absolutely revolutionary. I mean, without interrupts, modern graphical interfaces with a mouse and windows, totally impossible. Your computer would literally never know you moved the mouse until it decided it was time to check. Okay, so we've solved the nagging problem, which is great, but that just creates a new challenge. Now that you have all these different devices trying to talk to the CPU, you need a set of rules. You need a protocol for communication. All of this communication happens on what's called a bus, which you can just think of as a shared highway for information. And any conversation on this highway follows this really strict 4-beat rhythm. First, the CPU calls out an address, like a house number. Second, it says whether it wants to read or write information. Third, the actual data gets moved. And fourth, the conversation ends, which frees up the highway for the next car. But wait a minute, this brings up a huge question, right? If the CPU is just shouting out addresses onto this shared highway, how does it know the difference between address 500 in its main memory and, say, a printer that's also been assigned address 500? That could get really messy really fast. Well, engineers came up with two main ways to solve this. The first is called memory mapped I/O, which basically just pretends that everything is a memory location. This is simple, but it means your printer is taking up valuable memory real estate that your programs could be using. The other way, which the 8086 used, is I/O mapped I/O. This creates a whole separate address book just for your input and output devices. It keeps your main memory clean, but it does mean the CPU needs special instructions to talk to it. So you can see it here visually. With memory mapped I/O, all your devices are just kind of slotted right into that big block of main memory. But with I/O mapping, you get two totally distinct spaces, a big one for memory and a smaller, separate one for I/O. Think of them like two different neighborhoods. Okay, so interrupts and clear addressing. These things solve a ton of problems. But there was still one final bottleneck. What happens when you need to move a lot of data? Right. Imagine moving a huge file from your hard drive into memory. Even with interrupts, the CPU still has to act as the middleman for every single byte of data. It has to pick up a byte, carry it over, drop it off, and then do that again and again, millions of times. For huge files, this just grinds the processor to a halt.
And the solution to this was another brilliant specialized piece of hardware, the Direct Memory Access Controller, or DMA. Here's the best way to think about it. The CPU is like a highly paid CEO. You wouldn't want your CEO running down to the mailroom to make photocopies, right? No, you'd hire an assistant. The DMA controller is the CPU's hyper-efficient assistant for moving data. And the process is just beautiful in its simplicity. The CEO gives one single instruction: move this entire file from the hard drive over to this spot in memory. And then, the CEO goes back to doing important CEO things. The DMA assistant takes complete control of the system bus and handles the entire transfer, all by itself directly. And when the job is finally done, it just rings the CEO's doorbell. It sends an interrupt to say, "Hey boss, all finished." And this architecture right here is what makes our modern systems so ridiculously fast. With the data now flowing directly from a device to memory, the CPU is completely free to do other things. This is true multitasking. And it's the secret sauce behind fast game loading times, smooth 4K video playback, and quick file transfers. It is all happening in the background thanks to this amazing, dedicated assistant. So let's just take a step back for a second. When you put all these pieces together, this whole evolution from constant nagging to polite doorbells to personal assistants, you don't just get a faster computer, you get a fundamentally different kind of machine. We've seen this incredible journey, right? We went from a CPU that wasted all its time just checking for things to one that could be politely notified by a doorbell, and finally to a CPU that could delegate huge chunks of boring work to a trusted assistant. And here's the real key takeaway. These concepts that were developed for chips like the 8086 over 40 years ago, they aren't obsolete. They are the foundational invisible symphony that is playing inside your phone, your laptop, your console right this second. Interrupts are the cues from every instrument in the orchestra, DMA is the tireless rhythm section holding it all together, and the CPU? The CPU is the conductor, finally free to focus on the melody. It's this symphony that makes our seamless digital lives possible. It's the reason everything just works all at once. Which really makes you wonder, doesn't it? What's the fundamental dilemma that engineers are trying to solve today? And what incredible new capabilities will its solution unlock for us 40 years from now?